Hello, in today's video, I'll be solving questions on A2 reaction kinetics from May-June 2024, paper 4-2. Question 5, A. Nitrosyl chloride, NOCl, can be formed by the reaction between nitrogen monoxide and chlorine, as shown. 2NO plus Cl2 giving 2NOCl. The initial rate of this reaction is investigated, starting with different concentrations of NO and Cl2. The results obtained are shown in table 5.1. Table 5.1 is given as seen. I. Use the data in table 5.1 to deduce the rate equation for this reaction. Explain your reasoning. There are two reactants in this reaction, NO and Cl2. So it means the general rate equation is equal to K, which is the rate constant, times the concentration of NO exponent X, which is the order with respect to NO, which we don't know yet, times the concentration of Cl2 exponent Y, which is the order with respect to Cl2, which we don't know yet. To be able to write a complete rate equation, we need to find this X and Y, which are the orders with respect to the concentration of NO and Cl2 respectively. To do that, we first of all take two experiments. So in this case, we are using experiment 1 and experiment 2 first. We can see that in experiment 1 and 2, the concentrations of Cl2 are constant. So it means that in this case, we can deduce the order with respect to NO whilst we eliminate Cl2 since their concentrations are not changing. We can see that from experiment 1 to experiment 2, the concentrations of NOCl has increased. The same way the rate has also increased, but we don't know by how much, so we have to find that. So we divide the bigger concentration by the smaller, so that will be 0.075 divided by 0.025. And then for the rates, we divide the biggest with the smallest. So that will be 3.32 times 10 exponent minus 1 divided by 3.68 times 10 exponent negative 2. When we do this, for the concentration of NOCl, it has increased by times 3 and the rate has increased by times 9. This means that when you double the concentration of NOCl, you get the rate. And so it means that it is second order with respect to NO concentration. So we can say that in experiment 1 and 2, the concentration of NO is increased by 3 times and the rate also increases by 9 times. Therefore, it is second order with respect to NO concentration. Now let's find the order of reaction with respect to Cl2. So you have to use two equations. Now you can see that there is a challenge with finding the order with respect to Cl2. Because when we started finding the order with respect to NO concentration, it was easy to use experiments 1 and 2 as the concentration of Cl2 in experiments 1 and 2 are constant, so we could easily eliminate Cl2 and then easily find the order with respect to NO concentration. But this time around, finding the order with respect to Cl2, there is no two concentrations for NO that are the same. So that means that we have to just use two experiments where the concentrations of NO are different. So I'm going to use experiment 1 and experiment 3. We are going to divide the values in experiment 3 with experiment 1 as the values in experiment 3 are bigger than those in experiment 1. So for the concentration of NO, that will be 0.05 divided by 0.025. That of Cl2 will be 0.06 divided by 0.15, and the rate is 5.89 times 10 exponent minus 1 divided by 3.68 times 10 exponent minus 2. The concentration of NO was increased by 2 times, that of Cl2 was increased by 4 times, and the rate has increased by 16 times. Now, if you consider the general rate equation, which is rate is equal to K times the concentration of NO, and in this case, the concentration of NO, the order with respect to NO concentration is 2, times the concentration of Cl2, and we don't know this order yet, so I'll still leave it as Y. We can see that to find the order with respect to Cl2, we can make the Cl2 concentration exponent each order the subject, and that will be equal to the rate divided by K times concentration of NO exponent 2. Now, K is a constant, so I'm going to eliminate that out of this calculation for now. So that will be NO concentration exponent 2. So at this point, the concentration of Cl2 is the same as the change in concentration of Cl2, which is 4, and that will be 4 exponent Y, which is equal to the rate was 16 times divided by the concentration of NO is 2 exponent 2. So which means that 4 exponent Y is equal to 4, and any number can be raised to the power 1. So it means that Y is equal to 1. And so therefore the order with respect to Cl2 is 1. So it's first order. So we can say that in experiments 1 and 3, the concentration of NO was increased by 2 times, that of Cl2 was increased by 4 times, and the rate increased by 16 times. Therefore, it is first order with respect to Cl2 concentration. And so it means that our rate equation is equal to K times concentration of NO, and the order we calculated was 2 times the concentration of Cl2 exponent 1. So it's first order, and exponent 1 we can leave it as this. II. Use your rate equation from AI and the data from experiment 1 to calculate the rate constant K for this reaction. Include the units of K. So the rate equation was R is equal to K times concentration of NO exponent 2 times the concentration of Cl2. To find K, we make the K the constant. So that is K is equal to R over concentration of NO exponent 2 times concentration of Cl2. From the experiment 1, the rate is 3.68 times 10 exponent negative 2 divided by the concentration of NO is 0.025 exponent 2 times the concentration of Cl2, which is 0.015. So it means that K is equal to 3925.33. And for the units, we saw that the rate was in mole per decimeter cube per minute. And the concentration of NO was mole per decimeter cube, but this is exponent 2 times the concentration of Cl2, which is mole per decimeter cube. And so this will mean we have mole per decimeter cube per minute over mole squared decimeter minus 6 times mole per decimeter cube. So we get mole per decimeter cube per minute divided by mole exponent 3 decimeter minus 9. And so it means we get mole exponent 1 minus 3 decimeter minus 3 minus negative 9 per minute. And when you do that, you get mole exponent negative 2 decimeter 6 per minute. B. NO2Cl is another compound containing nitrogen, oxygen, and chlorine. In sunlight, NO2Cl can undergo homolytic fission to release chlorine radicals, which can catalyze the conversion of ozone, O3, into oxygen. Complete the mechanism for this process. The first one is the initiation step. In initiation step, a neutral molecule is broken in the presence of sunlight homolytically to produce two radicals. So remember, we have chlorine radical. It means we have chlorine radical plus NO2 radical. In the next step, we were told that chlorine radical catalyze the conversion of ozone into oxygen. So it means that in propagation step 1, we have to use our chlorine radical, which will react with the O3 to give us oxygen. So that will be ClO, and it's a radical plus O2. In propagation step, you have one radical at the reactant side and one radical at the product side. In propagation step 2, we need to use this radical produced in propagation step 1. So that will be ClO radical plus ozone, O3. Remember, in this reaction, we are producing oxygen. So it means that we are going to get chlorine radical plus oxygen. But mind you, the oxygen here was given to the O3. So that means we actually have O2 plus O2 being formed. And so that will be 2O2. C. Ozone reacts with nitrogen dioxide as shown in this equation. O3 plus 2NO2 giving N2O5 plus O2. The rate of reaction is first order with respect to O3 and first order with respect to NO2. Suggest equations for a two-step mechanism for this reaction. So anytime you have a two-step mechanism, the first thing to do is to react the reactants in the equation together. So we have O3 plus NO2. This will give us NO5. NO5 is an intermediate, so intermediates will be used up to form a product. So the NO5 plus, remember there were 2 moles of NO2, but we have used only 1 mole. So you have to use that second mole in our step 2. So that will be NO2. And this gives us N2O5 plus O2. Remember, the products are N2O5 plus O2, but we didn't form those products in the first step. And so this intermediate helped us to form those products. We can also use an alternative method. In this method, we have the ozone reacting with 1 mole of the NO2 to give us NO3 plus O2. Remember, there was O2 in the product, so we have formed O2 in our first step. But we need to form the N2O5 in our second step. And so we use the NO3 plus the second mole of the NO2 over here. And that gives us N2O5. So you can see that we have formed the O2 in the first step and the N2O5 in the second step. This NO3 is an intermediate because it was used up in the second step. In case you have to deduce the rate determining step, it is going to be step 1 because we can see that the stoichiometric amount of ozone and NO2 corresponds with the order of reaction with respect to ozone and NO2, which is first order and first order with respect to NO2 and ozone. Thank you for watching. See you again in the next tutorial. Please subscribe.